Cindy Rush, who will be talking about approximate message passing. Since this talk is a live talk, the questions from the live audience are more, relaxed, just call out a question whenever you have it. But if you're as part of the Zoom audience, same thing goes for you actually as well. You can unmute yourself and ask a question whenever you'd like. So barring a landslide of questions, let's plan to handle the questions from Zoom audience.
Okay, thank you. All right, hi everyone. I'm Cindy. So today I'm going to talk about approximate message passing algorithms generally. You guys can hear me with like the mask and the microphone, right? Okay. Cool. So what I'm going to do today in the lecture, I'm going to roughly follow along a tutorial article that I just wrote with my co-authors, Oliver Fang, Ramji Venkataramanan, and Richard Samworth, all from the University of Cambridge. Today when we go through what I'm going over, some of the math and these sorts of things, I'm going to try to give kind of heuristic proofs or some intuition for some of the mathematical aspects of the approximate message passing algorithms, and it won't be rigorous at all. So if you want to see the rigorous side of things, it's all there in the tutorial article that's like 100 or something pages. So whatever I do today, if you want to really see the real deal, that's the place to go. Okay, so just to begin with, what is approximate message passing, or do these algorithms mean for us? So in short, approximate message passing, or AMP, is a class of iterative algorithms that can be used for a number of things, but probably most relevant to this audience is that they can be used for establishing computational limits of statistical estimation problems. And so that's what we're going to talk about for the first half of my talk today, is just how can we understand computational limits through approximate message passing. So some, of the statistical estimation problems that AMP has been used to study are things like high dimensional linear regression or compressed sensing. This is sort of the original problem. It was studied for phase retrieval and other generalized linear models, and then also low rank matrix estimation. And so we're going to touch on each of these sorts of estimation problems throughout the talk. Okay, so the reason that, two of the reasons that we like AMP, two of the attractive features that kind of make this useful is AMP algorithms easily use prior information on the signal. So it's easy to kind of tailor the algorithms to exploit whatever knowledge you have about the signal. So I'm thinking things like, in low rank matrix estimation, right? You might know that the signal generating the low rank matrix is actually sparse, and so it's easy within the AMP algorithms to exploit that information. The other nice thing about AMP algorithms is that they have precise asymptotic performance guarantees in the form of like statistical characterizations of the iterates of the algorithm. And in particular, the asymptotics that they study is this regime where, if we have n as our sample size and d is, the dimension of the problem, then both of these parameters are growing in such a way that their ratio approaches some constant value, right? So this is the asymptotic regime I'm going to be thinking about during the next 2 hours of the lecture. And so what can we do with AMP, right? Well, the point 3 is what we're going to mostly focus on, but there's a lot of nice things. So Michael Celentano's work shows that you can use AMP to obtain lower bounds on estimation error of first order methods. It also gives you a precise asymptotics for various statistical estimators, which is something that I'm hoping to get to in the second half of the talk. And then, as I mentioned, in some problems, it helps us understand statistical computational gaps. And so this third point is what we're going to focus on now. Okay, so so normally when you start reading papers on approximate message passing, the ideas are originally presented through some derivation from a belief propagation algorithm. So the idea is you have a problem like compressed sensing. You write down a factor graph representation of the problem. You write down a belief propagation over that factor graph, and then you make some approximations and sort of outputs the AMP algorithm. And so the papers I've cited here have given those belief propagation type derivations for AMP algorithms for the various problems. And so while that sort of derivation from belief propagation can be useful and when you're doing analysis of the algorithms, and it can be insightful, it's not strictly necessary if we just want to understand sort of how to look at phase transitions or how to look at these sort of asymptotic statistical guarantees for the algorithms. So instead of actually deriving AMP from the belief propagation, like these works have done, I'm going to take sort of a different approach, which is that I'm just going to write out a standard AMP recursion that's not associated with any sort of statistical estimation problem. It's basically just a recursion on Gaussian matrices. And then we're going to study the statistical properties of the simple recursion, and then show how all these other problems kind of just, you can reduce those AMP algorithms back to the standard sort of simple basic AMP recursion. So the idea is I'm going to give sort of a basic AMP, and then from that we'll build until we get all of these sorts of specialized AMPs for various problems. Okay, so as I mentioned, right, the starting point of our development for today is going to be just an abstract AMP recursion that is not related to any specific estimation problem. And then what we're going to see is that the empirical distribution of the coordinates of each iterate of this like basic AMP is going to be approximately Gaussian, and then the properties of that Gaussian are going to be determined by a state evolution. And so the idea is if we can kind of understand the statistical properties of the really vanilla AMP algorithm, then when we look at these more complicated AMP algorithms, we'll just kind of reduce it back to this vanilla result. Okay, so the outline for the talk, I'm going to start by just giving the standard AMP. This is going to be I'll start with a symmetric recursion. So we're going to look at symmetric Gaussian random matrices, or GOE matrices. So in the first part of the talk, every W matrix is going to be an M by N matrix that's symmetric. So the elements above the diagonal are going to be normal with variance 1/n, and then on the diagonal also normal, but with a different variance, right? So this is just a symmetric Gaussian matrix. Then we're going to look at the high dimensional properties of the simple recursion using the state evolution. And then at the end, we'll connect the standard AMP to low rank matrix estimation, and then discuss some further extensions and generalizations. Okay, so here's the basic AMP algorithm that I want to study. So the idea is the following. So we're going to initialize our algorithm with some deterministic or random vector h0. So h is a length n vector, and this vector is going to be independent of my GOE matrix W, right? So now I have two objects. I have my matrix W, which is my symmetric Gaussian matrix, and then I have an initialization that's a vector independent of it. And so in the standard AMP algorithm, what we're going to do is we're just going to, sort of recursively define a sequence of iterates, H1 through, HT, let's say, that are defined in the following way. So, HT plus 1 is the sum of a matrix vector product, right, where we have our GOE matrix, and then our vector is going to be some function acting on the previous iterate. And then we're going to correct that with another term that's the product of a scalar value lambda, and then my previous sort of function acting on the iterate just before. So in this recursion, right, what do we have? So I have some function here, ft, that I'm thinking about this as being a scalar function that acts coordinate-wise on its vector input, right? And I'm just going to assume that it's just some Lipschitz function right now, right? And then I have a scalar term that's just defined in terms of the average of the derivatives of this Lipschitz function, right? So at this point, I'm not thinking about any specific estimation problem. I'm just thinking about a recursion on Gaussian matrices. Okay. All right, so what I'd like to do is, can we understand the properties, the statistical properties of this vanilla AMP, right? I'm thinking of this as a recursion, right? So these are vectors that are computed this way. So each.
So ft is just ft is a scalar function, so you apply coordinate wise.
Yeah.
Okay, and here you apply to each. Okay, here you just apply to each coordinate, and you just sum up.
Right. Yeah. So the scalar, right? Vector matrix. Okay. Okay. So the first question is, right? Can we say anything about the statistical properties of this iteration? And it turns out that we can. And so the way that we do that is through something referred to as a state evolution. Right? And so the state evolution is just going to be a deterministic recursion that actually tells us something about the performance or the sort of properties of the standard AMP. Right? So what I'm going to do is define the state evolution, and then we'll get to the sort of theoretical guarantees. And so the state evolution looks like the following. So the first thing we do is we set our tau 1 squared as a limit based on our initialization. So our initialization, right, is this H0. We assumed it was independent of the matrix. And so now I initialize with some limiting value of that initialization.
What's this parameter in the limit? What are you taking the limit over?
Oh, sorry, this is the parameter n, right? So I have my vectors H0. These are linked n vectors. My matrix is an n by n matrix. So this is the problem size. Right? Okay, and so one of the things I'm going to do is just assume that this limit exists. So nothing crazy is happening there. And then I have another recursion now, right? That's just a deterministic scalar recursion based on this function that I'm using in my standard AMP, and then some independent Gaussians.
Sorry, so H not is random, and is tau? Should I think of tau as random, or is tau this limit you're some converges with hyperability to, or converges to a number?
Yeah, so this is a deterministic value. So yeah, so you can think of, I mean, H naught can be random or deterministic. I mean, I think it's easiest if we just, you can think of it as like a vector with IID elements or something.
Okay.
What is the second thing? It's tau what?
Tau t plus 1 squared is equal to the expectation of our function that we use in the recursion that takes as input tau t, so the previous value, and multiplying a Gaussian random variable. So expectation with respect to the Gaussian. Okay. Okay, so now with this, we're ready to give the main theoretical results. And before I do that, I'm going to define something called a Pseudolipschitz function, because the theoretical results are given in terms of such functions. So a Pseudolipschitz function is just a generalization of the notion of a Lipschitz function, right? So I'm going to say a function psi is in Pseudolipschitz of order k with a constant c if this property holds. So essentially a function is Lipschitz if it grows like, one constant times x to the k is Pseudo-Lipschitz if it grows like that. Okay, so then the theory is the following. So if we assume that our matrix is GOE, so symmetric Gaussian, right, independent of our initialization, we also need to assume that the empirical distribution of our initialization as input to our function FO converges. So this is just so that my first tau1 over here is well defined, right? I also need some bounded moments on this condition. And then with some regularity conditions on FT beyond just the Lipschitz property, but are unimportant. What we see is the following. We get our main theoretical result. So this says for any Pseudo-Lipschitz function psi of order k, for every iteration of our algorithm, we get the following. So the average of psi acting on the elements of the iterates converges to a deterministic limit that's an expectation with respect to these taus, which are determined by the state evolution, right? So this is the tau t just from state evolution. This is just, an independent Gaussian random variable, right? So basically what this tells us is, if we have a Pseudo-Lipschitz function that we're interested in, then we can determine the high dimensional properties of the iterates of the AMP algorithm based on these state evolution values, right? So as an example, right, we might consider something like the function psi of x equals x squared, right? In which case, this result tells us that the limit of the 2 norm of our iterates at time t converges to tau t squared, which is the value given by state evolution.
If not to be linked since there is the other.
Sorry, yes. Yeah. Right. Right. Thanks. Okay.
And so this convergence again, it's only on n and for all t.
This holds for all t, right? And the limit is with respect to the problem. Okay. So, okay.
So basically, the way we should think about it is that we can imagine that after the t steps of the evolution, this is more or less like normals with that more or less behaves as if it was independent normals without the standard deviation.
Exactly. So my first remark is kind of to this point. So there's a lot of different notions of convergence that we can kind of show. So here, whoa, look at my Facebook. Sorry. Should have closed my eye. Okay, so what I presented there was in terms of almost sure convergence. So the first thing I wanted to mention is we can kind of strengthen the convergence to complete convergence automatically, which if you're not familiar with complete convergence, it's not particularly important, but somehow it seems to be the correct notion of convergence we're using here. And it just says that, we have a sequence xn that converges completely to some deterministic value x. If yn, which is any sequence such that xn is equal to yn distribution for all n converges almost surely to x. And so then once you've shown this complete convergence, what you get is actually a uniform convergence over Pseudolipschitz function. So instead of, for every Pseudolipschitz function, you can show the convergence uniformly, from which you can actually get a result about the empirical distribution of the elements. So this is kind of what I think you were getting at earlier. The kind of easier way to think about these convergences is not through the Pseudolipschitz functions, or I think at least, but and through statements about empirical distributions of the elements. So we have a vector HT, and what we've shown is that the empirical distributions of its elements converges completely in W2 to a mean zero Gaussian with variance determined by the state evolution. So what you can kind of think of then is that, this vector HT for my standard AMP has elements as if, they were drawn from this Gaussian distribution, right? So, empirical distribution of the elements, I'm just thinking about like the histogram of the elements. It's going to look as if it's a histogram. How this, I'm formatting on me, sorry. It's going to look as if it's a histogram of Gaussian draws.
So this particular thing doesn't preclude maybe the first element, like the odd elements being correlated with the even element that just came before them, but globally the histogram will look like it's Gaussian.
Yes, I think that's correct, right? So, all we can prove is exactly this statement. Okay. So a second remark is that,
Can I
Sure, sure.
something to, actually you can rule out that you can prove that if you fix any k coordinates, then the joint empirical distribution of any fixed k coordinates converges to the product. And the reason is that, by just the nature of the problem, the vector is exchangeable. You can permute it. So, for example.
Yes. So in some sense, you really could basically imagine that if you imagine that at stage t it's an IID Gaussian distribution with standard deviation tau t, you would not be you'd expect that any predictions you made under these assumptions would hold.
The prediction that you cannot make is saying something like the first coordinate is a strange, or a sublinear fraction of coordinates can be a very strange, in fact, a random sublinear fraction.
Okay. The second point I wanted to make is that we can also extend the results to a joint distribution over the iterates of the AMP algorithm. So, before, right, we were looking at some Pseudolipschitz function just acting on the elements of HT, my teeth sort of iterate in my AMP. But in fact, we can take a Pseudolipschitz function that, takes T inputs, right, and get a result here, right? And so the difference now is, on the right-hand side, this is still a deterministic limiting value that depends on the state evolution. But now we have to sort of define the covariance structure of these Gaussian matrices. And it's not, the covariance structure isn't important, but the short sort of takeaway is that it's also determined by the state evolution as well. So this covariance matrix of these limiting Gaussians is also defined recursively. The covariance matrix at time t is the matrix that adds a row and a column to the covariance matrix at times t minus 1, where these values again are determined by something that looks like the state evolution. The actual values are not important, but the point is that we can characterize the joint distribution of the iterates of the AMP as well. Okay, so what I wanted to do is try to give a sketch of the proof. So again, the proof is pretty technical. It's an induction on the iteration number. So we aren't going to go through the whole thing, but I want to try to give kind of a high level sketch so you can see where these values are coming from. So to do this, I'm going to start with just the first iterate. So you remember, let's see here. Oh, I can do this. Okay. So when we looked at our AMP algorithm, we had the H1. So this is, the T equals 1 iterate. It equals W, our GOE matrix, times our function F0 acting on our initialization, minus a scalar term times now a -1 term here. But when I define this algorithm, I'm assuming that negative indices equal 0. So this term this drops away. So in short, what I have is for my first iterate, it's just going to be the product of a matrix with a vector. And we know that these two are independent, right? We assume that our initialization was independent of the matrix W. So we can characterize this, the statistical properties of this exactly, right? So in particular, if we think conditional on H0, since H0 is independent of W, we have the following, right? W times F0 of H0 is just going to be normal, right? Because W is normal, and now conditional on H0, we have a deterministic vector there, right? Where the mean is 0, and the variance is almost the identity. But there's one additional term that just comes from the symmetry. Okay, so right. So what's the takeaway here, right? So when we look at this distribution, okay, so this is a deterministic value because we're thinking conditional on our initialization. So we have some value times the identity, and then we have a kind of rank 1 perturbation to that identity covariance that just comes from the fact that our W matrix is symmetric. And so if we want to analyze sort of the asymptotic properties of this, right, where we're in this asymptotic setting where n is going to infinity, then we can just study these two terms, right? And so it turns out that, the first term just converges to tau1 squared by assumption, right? So this term here, 1 over n F0 H0 squared converges to tau1 squared. Maybe I shouldn't use arrows as my bullets if I'm going to use arrows there. Right, so this converges to tau1 squared, my state evolution value by assumption. Right, and then this order 1 term, or sorry, this rank 1 term is just negligible in the limit. Right, so this kind of goes away. So again, we're just going to kind of ignore that. So what we've shown, right, is conditional on our initialization, then we have that H1 is like normal 0 with this sort of variance, right, with the variance given by tau1 squared. So what we've shown, right, is sort of kind of motivating this first statement that we have up here. Okay, so the reason that was easy was because this term kind of dropped out. So we just had our matrix vector multiplication, right? And it was also easy because the vector we were multiplying by the matrix, these guys were independent, right? The W was assumed to be independent of my initialization H0. But what happens is that, if we look at H2, right, H2 is going to be W times F1 of H1, right? And we're no longer going to have that independence because H1 was constructed by W here, right? So when we sort of, this notion, this step 0 sort of proof doesn't continue. But
You can condition on the first vector and just look at the randomness orthogonal.
yes, so this is essentially what we do. Okay? So let's look at the induction step, right? So, okay, what do we have when we have the induction step? So we're looking at HT plus 1 equals, again, our matrix multiplied by FT acting on HT minus our scalar value determined by the derivatives and the lag term, right? Okay. So, all right. So, what are we going to do, right? So, essentially, the idea is kind of what was mentioned. What we'd like to do is sort of decompose this matrix W along a basis that's sort of, determined by the previous iterates of the algorithm. So what I'm going to do is define a sigma algebra generated by H1 through HT, the previous iterates, and then look at the conditional distribution of W given that sigma algebra, right? So what's the distribution of W now that we've seen the values before? And it turns out that this is kind of the trick that allows us to analyze the recursion, right? And so this is an idea that goes back to Bolthausen originally, and then Bayati and Montanari did in their original sort of 2011 proof. But the idea is the following. So if we define, okay, our sigma algebra is ST, it's going to be the sigma algebra generated by H1 up through HT. Right, so this is the sigma algebra generated by the first T iterates. I probably should put the initialization in there as well, but fine. Then what I'm going to do is decompose W with respect to this sigma algebra. So I want to decompose my matrix W as follows. So what I want to show is that conditional on the previous outputs of my algorithm, my matrix W has the following distribution. So it's equal to a projection onto that sigma algebra, right? So the conditional distribution of W onto my conditioning sigma algebra, plus a projection perpendicular to the sigma algebra. So here, what am I saying? So I'm thinking of PT equals orthogonal projection onto the span of H0 through HT, and then this. And PT perp is just I minus that. Okay, so this is just true for any matrix, right? So what we're conditioning on, and short is sort of linear constraints on that matrix. So then we can decompose it into a part sort of orthogonal to those constraints, and then a part deterministic with respect to those constraints. Yeah. Yeah, so the M zeros instead of, yeah.
The projector, the state is the ages, but the projector is to the x of them.
Yeah, yeah, I see what you're saying. Yep. So this should actually be projecting onto F0, H0. Sorry. Okay. Right. Okay, and so then the kind of key part of this for us is that since our matrix W is a GOE matrix, right? It's symmetric Gaussian. It's also rotationally invariant. So what that gives us is that what we can do is replace the random piece that comes from the projection with a new matrix W hat where, or W tilde, sorry, W tilde is equal in distribution to my original W, but it's independent of my conditioning sigma algebra. And so this is kind of the key step, right? Is that here, we use the rotational invariance of the Gaussians to, now represent my random matrix W as a deterministic part, and then a part independent of my conditioning sigma algebra, right? And that's the projection outside of the sigma algebra as well, right? Okay, so let's see. Okay, so what does this actually give us, right? So what we've shown, right, is we have a representation for my matrix W equal in distribution conditional on my iterates up to time t. That's a deterministic piece plus a projection where the matrix and the projection is independent. So then this allows us to consider my iterate at time t+1 also sort of conditional on the previous iterates, right? So what I have here, right, is if we look at this sort of representation here, now what I'm going to do is plug in this for the W here, right? So what I get is that my HT+1 is equal in distribution to a deterministic piece multiplying by FTHT. My scalar correction term plus my projection term. And this is, yep. Great. Okay. So okay, so this is sort of nice, right? Because what ends up happening is, when we look at this, what we see is that this whole part up here is measurable with respect to my sigma field. Right. So this is all, conditional on the previous iterates. This is all deterministic, right? And then the part that's random, right, is random, but it's independent of everything we've seen before, right? So we have a new GOE matrix here that's independent of everything else. And so this is kind of you can kind of see where we're going here, right? So I'm going to argue inductively, right, that this deterministic piece, right, this is just going to be somehow Gaussian. That's the induction assumption. And then we get a new piece that's a new independent Gaussian. And so we can kind of add up all those Gaussians, and as long as we track the variance, we can see what happens. Okay. And so in short, this is a really sort of long proof, but the idea is that you look at that deterministic piece and kind of look at its structure, and you find that it looks something like the following. What you have is a sum of the previous iterates, right? So this is a sum of my HI, where I goes from 1 to t, so the previous iterates of the algorithm, combined with some alpha i's, whose value I won't state, but they're there. We get a new piece, like this is our perpendicular piece that's from a new Gaussian vector, and then we get some deviation term, right? So the idea is, you can show that this sort of representation that comes from our distributional properties of our GOE matrix gives us this form, right? And what do we have? Well, what we're going to argue is, these are Gaussian by induction. Right, we already showed the step 0 gave the Gaussian for H naught. This is going to be an independent Gaussian piece, right, that comes from our W tilde up there. So this is the part, outside of the previous iterates, but it's new independent Gaussian. And then this is going to be something that's just negligible. So, I can show something like the squared norm of this guy goes to 0. Okay, so the basic, the sort of technical part, right, is actually figuring out like what these guys are. So these are random, but what you can prove is that they have deterministic limits, and the values of those deterministic limits are given by the state evolution, right? So then what you end up with, right, is a sum of Gaussians where the components summing the Gaussians. You get an independent Gaussian piece, and this is also something we can determine by the state evolution. And then there's some deviation term that you have to argue doesn't matter asymptotically. But the takeaway, right, is that this essentially gives you what you want. Once you take kind of careful record keeping of all of these terms, you get this sort of
one HT minus 1 exactly cancels the least part, the expectation of
right. So what ends up happening, right, is you get some things up here that are, that go into kind of the Gaussian part, and you get some things that are non-Gaussian, and then this correction term, the Onsager correction term, is chosen so that it asymptotically sort of cancels out those non-Gaussian pieces. So it's essentially this choice here that gives you this going to 0, that ensures that we continue getting the Gaussian as we iterate the algorithm. Right. And let me see if there's anything else I want to say about that. And it's kind of like you can, if you go into the proof, you can see why this is right. It's Stein's lemma essentially that gives you the sort of result there.
So the HI should be the first term in FI is HI.
Say it again, sorry.
So the HI is the first term on the last line is FI or HI.
No, these are actually HIs.
What we are taking the conditional expectation is that to the signal field generated by I believe is F0, H0, F1, H1, FT, HT. So shouldn't the first term be linear in FI?
There's kind of a lot of steps between like here and here. So
you do some Taylor approximation. This is the linear contribution from the derivatives, which end up being constant or something like that.
We chose to find F of the previous one, right? So
You see, the conditional expectation with the row, the span of the rows of the will be a low rank matrix, and will be a combination of rank found components, and the rank found components will contain the F and the H's. Turns out that all the ones that contain the F are cancelled by the other terms. See this set. So the others are that she wrote.
Yeah, so significant or they just can ignore?
But all the others that are, some more, but they're all F's, and all the one proportional to x that are coefficient that is not zero are cancelled by the term which is central. Others proportional to f, but for the coefficient. I mean, I'm just repeating what she said.
Yeah. I mean, yeah, it's like say there are the f's somewhere in here, but it's, you know, it either gets subsumed here or the coefficients go to zero or something. So it's a, I mean, yeah, I don't know. The proof is really long, right? So you know, it's like quite a mess. But this is I'm you know, I'm hoping this is insightful, some sort of short takeaway. Okay, so I was, you know, okay, so what are we doing, right? So I wanted to give some kind of high level idea about why we can take a simple iteration like that and, you know, say anything at all about the statistical components. But, you know, that iteration I was looking at, it wasn't actually doing anything, right? It wasn't like solving any problem. All I was trying to convince you of is that if we just, you know, have sort of a matrix vector multiplication that happens in this way, then we can say something statistically rigorous about, you know, the output. And so what I'd like to do now is try to connect this standard AMP to an actual problem. And the actual problem I'm going to look at is this problem of rank 1 matrix estimation. And so the rank 1 matrix estimation problem is the following. So I'm going to imagine I have a model. So I have some data matrix A that I see that I'm modeling as the sum of a rank 1 piece determined by some signal vector V here and a GOE matrix. So here W is my GOE matrix as before, right? My signal sort of is defined by my parameter theta that just determines the signal to noise ratio in the problem, right? And also my vector V here, which I'm thinking is, again, some random or deterministic vector that's going to be independent of W. That's actually the signal giving the rank 1 piece in my rank 1 matrix estimation problem, right? And so the idea, right, is that we see A, right? And
So it's V unit norm or the entries?
I think you're reusing the letter V in the bottom.
What's the norm of V? Is V unit norm or is V norm squared of N?
so what I'm going to assume is that my elements of V are, it jumps like this, sorry. My elements of V are IID according to some distribution PV, right? And then, sorry, that's supposed to be if I have a capital V distributed as PV, then it has, so yeah, a capital V, but, okay, so it's clear?
Yeah.
We're good, okay. Right, so I have A, I want to determine V, or V, geez, right? Okay. So the first thing I'm going to do, right, is I want to do this by using an AMP algorithm. So how do I do this, right? So what I'm going to do is I'm going to try to use our standard AMP recursion that we looked at before, but I want to make it useful. And so, you know, when we looked at the standard recursion, it was a recursion with a matrix W, but now this matrix is my noise matrix and I don't see it. So I'm just going to write the same AMP algorithm that I was looking at earlier, but now I'm going to replace that matrix W that we don't know with my matrix A, that's the data matrix from the problem. Right. Okay, so this is the same recursion I was looking at earlier, but now, you know, instead of calling them H's, I've called them X, just to recall that now I have my data matrix there and not my GOE matrix. And so what we're going to do is, you know, try to appeal to my standard AMP results in order to say something smart about the distributional properties of this recursion. So the first thing I'm going to do is plug in my A. So since we know A equals theta over N VV transpose plus W, right? then what do we have? Well, we get that my recursion looks like the following. We get theta over n v, an inner product between v and ft acting on xt, right? Plus w times ft xt minus lambda t ft minus 1 xt minus 1. And so the thing we notice, right, is that, so now after we plugged in my model into the AMP with A replacing W, what do we get out? Well, we get out, you know, a recursion that has part of it, which is just the standard AMP recursion we looked at before, right? So this is, you know, sort of exactly the standard AMP. Plus a shift term, right? So now this is sort of like a shift. And so what we might want to do now is try to see if we can kind of guess the distributional properties of this recursion based on our knowledge of, you know, what happens with the standard recursion, right? So it turns out we can do that, right? So you know, how do we do it? Well, this we can characterize. We know, you know, it's looks Gaussian with mean or with variance determined by the state evolution. And then this is something, well, you know, this inner product, we can just appeal to like law of large numbers and get a concentration type thing there. So let's go through this. There's one little caveat. So what I'm going to do is I'm going to cheat a little bit. And so let's cheat a little bit and assume that I have an initialization for this algorithm that's correlated with my true signal. So I'm going to assume an initialization that looks like the following. So in practice, right? Well, we'll talk about it, but let me cheat for right now and say that I can initialize with something correlated with the truth. So here I'm thinking of Z0 being a vector of Gaussians independent of V, my signal. Okay. So if I do that, if I cheat and I initialize correlated with the truth, then I can look at analyzing this. So let's start in the same way we did before, right? By just looking at the first term, so the t equals 0 case. So if I look at the t equals 0 case like I did before, then what we see, right, is that this term is again going to go away because my negative indices are 0. So I just get something that looks like theta over n v times inner product v f0 x0 plus w f0 x0. Right, where again, x0 I'm thinking of as being correlated a little bit with the truth, right? And so what we find, right, is, you know, we can sort of analyze this. So the first point is that by law of large numbers, you know, assuming that V is IID PV, right? What do we have? This inner product. Converges to an expectation, right? So an expectation of V, F0, mu0, V plus mu0, V, right? Where V is a random variable distributed as PV. Right. And then again, you know, if x0 is independent of W, right, then W f0 x0 is like normal 0, 1 over n, norm of f0 x0. squared plus a delta term, which, you know, again, this guy is asymptotically. Okay, so, right, so we look at our x1, we, you know, can kind of argue that this guy is going to concentrate on some deterministic expectation. And, you know, this guy too, this is the same sort of analysis we did earlier. It's going to be Gaussian as well. And so what do we sort of show? Well, okay, what this gives us, right, is a result like the following. Okay, so I guess I'll do one more step, which is, you know, remind us that something like this will limit to something like and so putting this together, you know, putting together, what have we found? Well, we've shown that x1 will limit to something that looks like the following, where this mu1 is this guy. And then our sigma 1 is the square root of f0 squared. And so this is just putting these pieces together, right? So here, you know, we get that this concentrates on this expectation. So now we have x1 is equal to our true signal plus, you know, there, right? Theta times the limiting expectation, right? So this gives us the first term, right? Where the mu is that guy. And then the second term just comes from looking at this, which is our Gaussian piece, right? Okay, so you know, what we've shown is you know, how you could get something like this, right? Of course, this isn't a rigorous proof, but you know, you can take these ideas and sort of get to a statement of the following. And you know, if you go through sort of an induction argument like we did earlier, then what you can show is that you know, if you assume that your teeth iteration has this distribution, right? So motivated by what we just looked at for the first iteration, then you can show that your t+1 iteration has this distribution where the mean and the variance there are just updated by, you know, the way that we kind of motivated by looking at the first step, right? So, you know, again, right, you have to actually make the inductive argument, but it turns out that it works out just, you know, kind of like what we did here. We see the same form when we update the mu and the sigma as we go. Okay. Sorry, so these guys should be, the T should be in the air, right? Okay. Okay, so okay, so maybe since it's already past, we'll like take a break now and then I'll finish when we come back. Does that work? Okay, thanks.
Okay, are there any questions at this point for Sue?
So for the spike matrix problem, what would the F you choose be?
Yeah, so we'll talk about it a little bit more when we come back from the break. I didn't have I thought I'd get through more, so I didn't have a good stopping point. But essentially what you do is, you know, you can look at something like this, right? And if we know that my teeth iteration has this sort of distribution, what do I want, right? I want this to be large relative to this, right? So that I get mostly signal and only a little bit of noise. And so you can actually choose the F to optimize that signal to noise ratio. And the F that optimizes that comes out to be something that's proportional to the conditional distribution. So this is something we'll talk about in the next hour, but it's a good question. And it turns out you can calculate it exactly what you're optimal.
Okay, cool.
Is it possible to study non-Gaussian matrices?
Yeah, so theoretically, there's been a lot of study of non-Gaussian matrices. So if the elements are sub-Gaussian, for example, then Biaggi and Montanari and Large, studied sub-Gaussian design matrices. There's also been a line of work looking at rotationally invariant matrices. So this is like orthogonal AMP or vector approximate message passing. And Zhou Fan just had a recent paper along those lines. There's also been some extension. Chen and Lam updated the original Biaggi, Large, and Montanari results for sub-Gaussian matrices. So there's been a lot of work in this area, but it turns out if you change the matrix, things like the state evolution and stuff have to change a little bit too. So the recursions are slightly different, but you can still get the same source of.
This might be addressed later, but is there like a natural multi-vector generalization of this where I guess you track the state of like multiple vectors and there's some nice recursion that like lets you understand that?
Yeah, so I'll mention you can get an asymmetric version. So if your matrix W is not symmetric, but just IID Gaussian, and so then you get a two sequence recursion. And you can also extend that to kind of matrix iterates. And it turns out that the extension to the matrix iterates is useful because you need it to prove things like generalized versions of approximate message passing. So if you want AMP to solve like generalized linear models, for example. So there is an extension that has matrix.
So is there any way to motivate why this kind of iteration is working? Is it trying to solve any like fixed one problem or trying to estimate things, something like that? Or like what kind of problem this AMP algorithm will work? Do you have any intuition?
Yeah, so I mean it works well for problems where you have like a planet solution. So something like the lowering matrix estimation, right? You have that signal B that's generating your data matrix, or something like high dimensional linear regression where you have a signal X that's generating your data Y.
Is linearity very important here? Or
Is the what, sorry?
Linearity of the model very important?
What do you have in mind?
No, I don't know. I'm just asking.
Okay. I mean, I think so. I don't. What do you say? Linearity
no, if you don't have in mind.
Yeah.
I guess maybe like if say A instead of A of X being like matrix plus random plus noise, it would be you apply some I don't know, random quadratic to something plus. So the somehow the noise is not added in a linear way to the. So some quadratic operator or something like that. The natural thing would be like a quadratic iteration of the quadratic rather than a linear.
Yeah. So, like, I don't know. What do you think?
I mean, if you want to build a quadratic model for low rank estimation, in the end it ends up, being difficult to build a non-trivial model. But something that is non-linear is if you want to do tensor, low rank tensor estimation.
But you still have like an additive noise. You take tensor and the signal is like spike tensor, so it's still additive noise.
Well, another is generalized linear models, right? Then you have f of x times theta, and you
But it's still linear and, you know, it's AX that, even for the general, yeah.
It can have additional randomness.
Yeah,
Like, it can have additional randomness.
Yeah, so I mean, like, generalized linear models, right? You can kind of mess with the types of noise there, but. So I guess we have to merge there. Yeah, yeah, yeah. It's like if you give me a model, I got
Let's say something here. This is expected to work when expanding models.
The statement needs to be tempered by classical models where the signal is detectable by logically methods, right? Because AMP is of one Taylor approximation is codable by logical methods. No?
Yeah, I mean, I'm okay with that refinement of my statement, yeah. Yeah.
Even that is not entirely obvious, right? Because you can take F to be non-separable, right? I agree if F is separable, then you can approximate any one-dimensional function. Okay.
Non-separable?
Non-separable means a function from Rn to Rn, right?
Doesn't act on each coordinate separately.
Yeah.
What do you have in mind?
Projection on a set.
Or like if your signal has some dependencies between the entries, you wouldn't, you might not want to do either there.
Strong enough that there is not so.
A Turing machine.
Okay, so maybe we better say the rest.
Yeah, and then I'll.
We'll be back here at 8:14.